Hello ladies and gents. Today we're going to be talking about periodicity, which is essentially just looking at how things change as we go across the periodic table. It's good. It sounds very complicated and it always looks very complicated because it features a lot of graphs, but actually it's very simple. So we just need to make sure we keep boiling it back down to the basic differences between chemical elements. These are the specification points we're covering. You'll notice that part D is describing and explaining the variation of first ionisation energies, which is something we've actually already done. So we're going to be just quickly revising that and then focusing a little bit more on the other bits. Should be quite a quick video this week. So let's think about the periodic table. The periodic table is organised by increasing atomic number, so that's increasing number of protons. That's essentially where you get the order from. But it's a bit more complicated than that. It's also organised into groups, which are elements that have similar properties. These groups are then organised into periods, which are essentially a line of elements that have a repeating pattern. So they don't have the same properties. What they do have is the same trend in properties. So period 2 will have the same trend in properties as period 3. Period 4 gets a little bit more complicated because we've added in the transition metals, but period 4 will have broadly the same trend as period 5. And that is because of how similar the groups are. So periodicity is looking at these trends that we get across the period. What is the pattern? It's a repeating pattern. It's the same each time. In fact, one of the original chaps who tried to sort out the periodic table grouped the elements by octaves. He called them octaves, like in music where you have the repeating pattern giving you the same note every eight notes. In this case, it was the same element every 8 elements. So we have this general pattern that happens for the first 2 periods that we're going to be looking at, and that's because if you have the same groups, atoms in the same groups, so atoms in period 2 all have the same outer shell arrangement and then therefore have similar properties. They're going to bond in similar ways, they're going to react in similar ways, they're going to do a lot of very similar things. So let's start off with ionisation energy. So the top 2 graphs here are the first ionisation energies of elements in period 2 and elements in period 3. You'll notice these graphs are near enough identical. If we just jiggle the scales around, they could look exactly the same. You go up for a bit, then you go down when you get to the first electron going into the p orbitals. Then you go up some more. Then you have half a shell, so you go down again. But broadly speaking, we are increasing as we go across the period, and that is quite simply because we're increasing the number of protons. The difference between sodium and magnesium is 1 proton. The difference between magnesium and aluminium is another proton. The difference between aluminium and silicon is another proton. And this increasing number of protons increases the pull that the atom has on its electrons, and therefore increases the amount of energy you're required to move them. We also need to know about what happens to first ionisation energy as you go down the groups, and that is invariably they decrease as you go down the group, and that is because despite the fact, and it is important that you always note that you are increasing the number of protons, and therefore the pull, you increase the number of shells, and that increases the number of shielding, which counterbalances the number of protons, and therefore cancels it out and makes the ionisation energy decrease. Next thing we need to talk about is the atomic radii. So that's the size of the atom, the size of the nucleus. Now this increases all the way across the period in both cases. And that is because despite the fact we're adding more protons, so you think the nucleus is getting bigger, the size of the atom comes from where the electrons are. They're the things actually taking up all the space, despite the fact they are very small. And the more protons you have, the more tightly held the electrons are, the more they're going to be pulled in towards the nucleus, and as a result, the smaller the atom. So you can see the atomic radii decrease dramatically as you go across the period, for both periods. Simply more protons. Once again, the only difference between these elements, is that they have, as you go each space right in the periodic table, you get another proton. Therefore, you pull your electrons in tighter. Simple. Melting point and boiling point are a little bit more complicated, because now we're not talking just about increasing numbers of protons, we're talking about different types of bonding. You can see they follow a very similar trend. Both boiling point and melting point stick broadly to the same trend. And also, you'll notice that group period 2 and period 3 stick to the same trend. I'm sorry. But what we need to think about is the types of bonding here. Now, if you look at lithium and beryllium, they are both metallically bonded. Sodium, magnesium, and aluminium are all metallically bonded with increasing strength as you increase the number of protons. Therefore, you increase the number of outer cell electrons, so increase the number of bonds, you increase the electrostatic interaction. So that explains that increase. Carbon and silicon are both giant molecular structures, so they are very, very hard to break apart. They have strong covalent bonds between them. And then nitrogen, oxygen, fluorine, neon, and the same for phosphorus, sulfur, chlorine, and argon. They are all simple molecular. In fact, argon and neon aren't even molecules, they're just atoms. And they're relying on van der Waals forces to keep them together. Now, you'll notice that phosphorus and sulfur are much higher than fluorine, chlorine, nitrogen, and oxygen. And that's because phosphorus and sulfur hang around in much larger groups. Sulfur hangs around in S8 molecules, phosphorus usually P5. And that means there's more electrons there for more van der Waals forces. You can have greater induced dipoles. So melting point and boiling point are a little bit more difficult to explain, but you just have to boil it back to, if you'll excuse the pun, just boil it back to the different types of bonding that are going on. Are they giant molecular? Are they metallic? Are they simple molecular? Those are your options. Okay, have a little think about all of these three properties we've been talking about, because we're going to have to use those quite extensively next lesson to explain various properties. Thank you very much for watching. I shall see you on Wednesday.